In the last MEB video, I covered Hess's law, which says if a chemical reaction can be derived by an algebraic manipulation of a series of chemical reactions, performing the same algebraic manipulations on those heats of reaction will yield the heat of reaction for the reaction of interest. The problem, of course, is that Hess's law assumes that you know what the heats of reaction for the individual reactions are, and that may not always be the case. Oftentimes, it will not be the case. So this video will cover what to do when you do not have those heats of reactions. Before I tackle exactly how that works, I want to cover the topic of a formation reaction, which is a reaction that forms a chemical species from raw elemental species as they're oftentimes seen in nature. Let's take, for example, pentane, C5H12. What would the formation reaction be that produces pentane? Well, pentane is made up of 5 carbon molecules, and carbon is an elemental species itself. In nature, carbon is found as a solid with no diatomics or anything like that. It's a crystalline solid structure. So if 5 carbon molecules come together, you can link them in a chain which forms the backbone of pentane. You would also need some hydrogen molecules, and because hydrogen has an atomic number of 1, you would oftentimes never see hydrogen by itself. Hydrogen would always be H2 in nature. So to get to 12 hydrogens that are in pentane, you would need 6 hydrogens. And remember, for this chapter, we're always concerned with the state of the gases as well. The state of all the species. So hydrogen is in a gas state. Pentane is in the liquid state at room temperature. Because this is a formation reaction, the heat of this reaction is equal to the heat of formation for liquid pentane. This is useful because while the heat of reaction may not be tabulated or given, you have a table of the heats of formation readily available in your textbook. And this is a table that we have used before. So you may have noticed this, but we haven't highlighted it up until now. You can find these all in table B1. So there's a column in table B1 that has the heats of formation for these various species. And just like all the other heats of reactions that we've been talking about, you have to be aware of that these are at standard conditions, which for reactions are 25 C and 1 atmosphere. Okay, so how does this help? Well, if I have a reaction for which I want to figure out what the heat of reaction is, let's take, for example, the combustion of pentane. So the combustion of pentane would be C5H12 in the liquid form. So technically, this should be a vapor for a combustion, but we'll ignore that for now and say that we want to figure out what the heat of the reaction would be for combusting liquid pentane. And the balanced form would be 8O2, and oxygen would be in the gas phase, goes to 5 carbon dioxides, which is also in the gas phase, and 6 water molecules. We'll say water is in the liquid phase as well. Although again, typically for combustion, water would be in the vapor phase. But anyway, say we wanted to figure out what is the heat of this reaction. We're going to combine Hess's law with the heats of formation, as I've just defined above. So in order to get this reaction, I want to first take all the formation reactions. So the formation reaction that forms pentane, I already had from above. It's 5 carbon molecules, which are solid, plus 6 H2 molecules, which are gas, goes to a C5H12, which is a liquid. Oxygen, just going right down the line here, the second species is oxygen. Oxygen is already in its elemental form, right? So this is a trivial chemical reaction. This is not really a chemical reaction. So the heat of formation, these are all things I can look up, by the way. C5H12, delta HF for O2 is going to be 0. I don't even need to look that up. And that is, again, because oxygen is not formed. Oxygen just exists in nature as O2. What about CO2? I suppose you could make the argument that CO2 just exists in nature as well, but CO2 is composed of building blocks. I guess my point is that it cannot be the base building block. So I can't break up oxygen any more than I already have, but I can break up carbon dioxide more than I already have. It's carbon, which is again solid in its elemental state, plus O2 gas. That is the formation reaction for CO2. So I'm going to write this as delta HF for CO2. And finally, H2O in the liquid phase has a formation reaction from a 1 molecule of H2 in the gas state plus 1/2 molecules of O2 also in the gas state. And this is the heat of formation for H2O. I should be including the states of matter as well in these. All right, now from these chemical reactions, now I can use Hess's law. So how can I finagle these for blue reactions to get to the gold one? So C5H12 is on the reactant side of the first reaction, the one of interest that I want to calculate. Right, so I'm going to need to flip the first one. So I'm going to need to have minus delta HF for C5H12 liquid. So if I flip that one, I'm going to get C5H12 on the left-hand side. O2 I don't have to do anything with because, again, it's already elemental. But again, suppose for sake of argument that I flipped it and multiplied it by 8. So minus 8 times delta HF for O2, which is 0 anyway, but I'm building towards the derivation that will be useful. CO2, if I multiply this by 5, I'd get 5 CO2s. So plus 5 times delta HF for CO2 gas. And if I multiply the last one by 6, I get 6 H2Os. 6 times delta HF for H2O liquid. Now, if I did that correctly, everything else should cancel out. So in other words, I would get C5H12 goes to 5C plus 6H2, subtracting 8 times heat of formation for O2. So 8 O2 goes to 8 O2s. 5 times the third one, so 5 carbons plus 5 oxygens goes to 5 CO2s. And 6 hydrogens plus 6 times 1/2 is 3. 3 O2s goes to 6 H2Os. Now, if I cancel out everything, see, I've got 5 carbons there, 5 carbons there, 8 O2s. Let's see, do I want to cancel out those 8 O2s? No, I don't want to cancel out those 8 O2s. That's going to be important. I want to cancel out these 5 O2s and these 3 O2s with those 8 O2s. Well, I suppose I could have just canceled. I'm just going to cancel these two. That would be the same thing. I'm going to cancel these 6 H2s with these 6 H2s. Now, if I add up everything, once again, I got C5H12 plus 8 O2 goes to 5 CO2 plus 6 H2O, which tells me that if I combine Hess's law with the heats of formation, I can derive what the heat of that reaction is. So in much more general terms, you don't have to go through this thought exercise every time that you want to solve for a heat of reaction. You can simply derive the following formula that says the standard heat of any reaction is equal to the sum of the absolute value of the stoichiometric value, coefficient of the products times the heat of formation of that species. So we'll call that delta HF standard I minus the sum of the reactants, same quantity. The absolute value of the stoichiometric coefficient times the standard heat of formation. All right, so again, if I wanted to figure out what the heat of this reaction is, I would just say it is equal to this expression, which is exactly the general form of what I've written there. And if I wanted to figure out numerically what it would be, I'd have to look up the values of these 3 heats of formation, because I already know the heat of formation for oxygen is 0. I look up delta HF in table B1. All right, before I end the video, I just want to touch on another concept that is useful. For a combustion reaction, which is what that just was, I can more directly look up the heat of formation by looking up the heat of combustion. So heat of combustion is the heat of reaction for a combustion reaction. I also want to reiterate that the standard sign, so if I take the heat of combustion, this standard or the degree sign means that these are at standard conditions. The reference state for all these heats of reactions is once again 25 C in 1 atmosphere. So anytime you see a degree sign, know that that tabulated heat of reaction is for 25 C in 1 atmosphere. So I want to point out that heats of combustion are also found in table B1 for the combustible species that are in that table. Only for combustibles. And I just want to make a couple of quick notes about those heats of reactions. The notes I'll make are that one, that these are for complete combustions only for complete combustions. And recall that a complete combustion is one where CO2 is the only thing that's forming. So all carbon is forming CO2. All carbon forming CO2. All hydrogen forming H2O. So on and so forth. So you could also have all sulfur forming SO2 and all nitrogen forming N2. And the other weird thing about the heat of combustion in table B1 is that it assumes that water is formed in the liquid state. So if you have a combustion reaction where water vapor is formed instead, the heat of that reaction is not going to be equal to the value that you find in table B1. So this one is a bit counterintuitive. Because I would assume that in a combustion reaction, water vapor is usually formed. So in the context of figuring out what a heat of reaction is, you can do the same thing with the heat of combustion. The only thing you have to watch out for is it's the opposite of the last time. So I can write the following formula, that the standard heat of reaction for any reaction that I want to know is equal to the negative of the sum of the stoichiometric coefficient of species I times the standard heat of combustion of species I. So expanded a little bit, it's the sum of the reactants minus the sum of the products. And if you notice, if I compare the formulas for the heat of combustion to the heat of formation, let me zoom out a little bit to see them both. The heats of formation is products minus reactants, whereas combustion is reactants minus products. And that reflects the fact that in a formation reaction, the species of interest is on the product side. So we are forming all the products. In contrast, in the heat of combustion, the species of interest is on the reactant side. So that's why I have to flip all of them. So either one of these methods can get you what the heat of reaction is from either the heat of formation of all of them or the heat of combustion of all of them. And which one you use just depends on whether or not you have all the heats of formation or all the heats of combustion. So I'll point you to example 9.4-1 in your textbook if you'd like to see an example of how to apply this formula. Example 9.4-1. And that'll be all for this video. See you in the next video.